So this time I'll be talking about parsing with dynamic programs. In the reading we covered essentially dependency parsing with kind of graph-based methods. I'm going to be talking about that in the neural context, and also we're going to be talking about dynamic programming-based approaches to phrase structure parsing as well. And these can be also used not just for syntactic parsing, but anything where you want to generate a tree structure from a sentence. So here. So as we reviewed last time, there's two types of linguistic structure: dependency structure and phrase structure. And parsing is predicting linguistic structure from these sentences. And last time we covered transition-based parsing. And this time we're going to cover dynamic programming-based models that calculate the probability of each edge or constituent and perform some sort of dynamic programming. And this is analogous to the linear CRF model for part-of-speech typing. So just to very briefly go through the reading. In the reading, we talked about minimum spanning tree-based parsing models. And specifically, the reading mostly talked about first-order dependency parsing models. So essentially what this does is this expresses a sentence as a fully connected directed graph, like this. So you have one edge going between each of the words in the sentence. You score each edge independently. So each edge gets its own score, like -1, 7, -2, 3, etc. And then you find the maximal spanning tree using using some algorithm, which gives you this. So then is the head, and then this an example are children of that, and then n is an example, is a child of example. So graph-based versus transition-based. Transition-based, what are the advantages and disadvantages? Transition-based has the good advantage of being able to easily condition on infinite tree context. So this is essentially a structured prediction problem, just like machine translation. It's a structured prediction problem with like infinite context. So exactly like sequence models, we can use an RNN to condition on all the contexts that we've used so far. The problem with this, for example, neural MT models or things like this, is they may do very well locally, but because of the necessity to condition over long dependencies or do kind of search algorithms using greedy search or beam search, this can cause short-term mistakes. So graph-based algorithms, on the other hand, find the exact best global solution using some sort of dynamic programming algorithm. But in order to do this, they have to make local independence assumptions. So just like we made local independence assumptions for the CRF, where we only condition tags on the left and right tag, they have to make similar assumptions. So in first order graph-based dependency parsers, the assumption that they're making is basically that each edge, given the input, can be scored independently of all of the others. And I'll talk about why this can be a problem later on. But basically what you do is you take in your input sentence and you give a score to each edge before you even calculate which edges actually exist in the graph. So the Chu-Liu-Edmonds algorithm, I mean, this was covered well in the reading, so I'll just go through it very quickly. We have a graph. We want to find its spanning tree. So we greedily select the best incoming edge to each node. If there are cycles, select the cycle and contract into a single node and recursively call the algorithm on the graph with the contracted node. Then we expand the contracted node, deleting an edge appropriately. So find the best incoming one. Subtract the max for each node. Contract the node. Recursively call the algorithm, and then take the node and delete it from the cycle. That gives you a graph. So this was covered in the reading. Now I'm going to move into some stuff that wasn't covered quite as extensively, which is other methods for dynamic programming. These are good things to know, just kind of in the back of your mind. If you're interested in dependency parsing, you should definitely look these up and see what they are. One is Eisner's algorithm. So Eisner's algorithm is a dynamic programming algorithm to combine together trees in n cubed time. Unlike the Chu-Liu-Edmonds algorithm, it can create a projective dependency tree. So the difference between projective and non-projective was explained in the reading, right? Yeah. So as we know, non-projective dependency trees can have like crossed edges, etc. The Eisner algorithm basically is an algorithm, bottom-up dynamic programming algorithm that ensures that you can get projective dependency trees. There's also Tarjan's algorithm, and this is what people use in like serious graph-based parsers nowadays. It's like Chu-Liu-Edmonds, but it has better asymptotic runtime, but is significantly more complicated. So you can do this in n log n instead of quadratic time. Okay. So these are, if you know Chu-Liu-Edmonds, you can implement one of these things. But then the question is, what do you use for a training algorithm? The training algorithm, the easiest possible training algorithm is just to predict the value of each edge. So you run a neural network. For each node, you predict its head, for example. And that's one easy way to do it. But a way that has proven better, at least has proven significantly better in non-neural models, is to use a structured training algorithm using something like the structured hinge loss. And this was covered in our structured prediction class. But just in case you don't remember, basically what we do is we find the highest scoring tree. But when we find the highest scoring tree, we penalize each correct edge by a little bit. So we add 1 to the score of all of the edges but the correct edge, or we add -1 to the score of all of the correct edges. We find the best tree. And then if the found tree is not equal to the correct tree, we update the parameters using a hinge loss. So the good thing about this is basically this incorporates the whole end-to-end decoding algorithm in the training of your system. So it's also pretty simple because, of course, you're going to have to implement decoding anyway. So you could pre-train your model just to predict the correct edges, and then kind of fine-tune the model using this, where you run decoding, get the potentially wrong output, and then you downweight the score of that, and you upweight the score of your correct tree. So features for graph-based parsing. This is before we had neural network featureizers, but like anything else, it's a good idea to know these before you design a neural network model, so you're aware of the things that might be useful. So what features did we use before neural nets? And basically, it was these big feature templates. So you have things like unigram features, which are the part of speech tag of the word. The word for the parent, the word for the part of speech tag for the parent, combined together, or just the word, or just the part of speech tag. The word for the child, the part of speech tag for the child. And then they also have bigram features, which consider the parent and the child, etc. Actually, this says big-gram features. I kind of like that better than bigram. But, and then also features about the surrounding words, etc. So like for transition-based parsers, a lot of the effort went into designing these feature functions. And these can be conjoined with like the arc direction or the arc distance, etc., to come up with a score for each arc in your graph. They also used features of like combinations of post tags, etc. Another thing that people did before neural networks is if you had really long words, these tended to be sparse, so you'd only take the first 4 letters of the word or something to make sure that you get the root of the word only. So you can see that a lot of engineering went into these things. One thing to think about when looking at this is if we have a strong neural network model to predict these relations between these words, is it able to capture all the features that we had here? With word embeddings, maybe you can to some extent. It's not clear whether you could capture the part of speech tag directly from that, but maybe you could do it if you have an appropriately expressive model. So this was a description of features. One important thing to know is that there's also higher order dependency parsing methods. And higher order dependency parsing methods are essentially methods that don't make an independent assumption on the score of the edges when you're calculating the scores of the edges. So they consider multiple edges at the same time. So a first order dependency parser will provide a score for like saw and girl and saw and with. A second order parser will consider pairs of edges, like I saw girl, saw with telescope. And third order will consider things like saw girl with telescope, etc. So does anyone have an idea like why this would be a useful thing to have in disambiguating this particular sentence? Is there a particular second order or third order edge that looks useful in this case? What's that? Saw with telescope, yes, exactly. So if you think like, if you're seeing with something, you're probably going to be seeing with some sort of instrument that is used to do seeing, right? So saw with telescope seems like a pretty informative pair of edges to have. And you don't get that if you only do this here. So before neural networks, this higher order dependency parsing was really, really important. Basically, you would get much better results if you had these second order edges in here, because it allowed you to figure these things out. So a really good benefit of this is you can extract more expressive features. A really large disadvantage of this, though, is if you consider all pairs of words in the sentence, obviously a graph-based dependency parser is n squared at the very least, right? You need to calculate the score of all words being heads of all other words. If you get to second order, now it's n cubed, because you need to consider all pairs of edges. And that's not even considering the algorithm that you use to search for things. So the algorithm that you use to search for things is going to be even more expensive. But this is an important thing to know, and I'm going to talk about it briefly later when we talk about neural models as well. Okay. So are there any questions so far? Okay. So neural models for graph-based parsing. The structure of this is actually going to relatively closely follow the structure of what I had last time, because the evolution of the models in transition-based parsing and graph-based parsing is somewhat similar. So the first kind of methods that were used to perform graph-based parsing were neural feature combinators. So basically, they would extract the traditional features, but they would let the neural network do the feature combination. So this is similar to the transition-based model. Also, learning from this paper, they used a cube and tanh activation function. They also used averaged embeddings of phrases, and second-order features. So these are some things that they used here. The phrase embeddings was that the motivation is that the words surrounding or between head and dependent or head and child are important clues. So the way they represented this was essentially if you had the head, you had the dependent here. They would calculate a prefix embedding, which was the average of some of the words before. the infix embedding, which was average over all the words in the span here, and the suffix embedding, which was the average of all the words after up to a certain amount. So their results were quite good. They improved the labeled attachment score from the previous state of the art from 90.39 to 91.37, 91.06 to 92.13. And the speed was relatively fast, reasonably fast. The second order neural parser was already better than a third order non-neural parser. So this was showing that, interestingly, if you have better, essentially, feature combinations, you can do better than better feature combinations, better way to express features through neural networks. This allows you to do away with some of the structure that was really important in the previous models. So the next thing, the overall theme of 2016 comes up again, put an LSTM on everything. So basically, they made the model even simpler. You just take an LSTM, you run a bidirectional LSTM in both directions. You extract these as the feature for each word. And then you have an MLP that takes in the word itself and and any other word that might be in a relation with it, and use this to calculate the the edge scores. So then this model was further extended into by using a bi-affine classifier. And basically, this model, despite being from 2017, is still a pretty standard model that a lot of people use for this. The reason being that this is a quite simple model that's also very strong and works very well. So the way it works, it's simple, but I'd say it's somewhat clever, is simply this. And I'll go through each of these one at a time. So basically what you do is for each word, RI, this is a word embedding, you run it through an MLP for the dependent. You run it as a dependent. You run it through an MLP as a head. And then based on this, you take the dependent representation, a matrix here that does a linear transform of the dependent representation, and calculate the score of each arc for each dependent. And then you also take the representation of the head and multiply it by a mate vector here. So this is, to unpack this a little bit more, basically what this is doing is the first term here is calculating how likely each vector is as a head of this particular word. And this second term here is calculating how likely each word is as a head, period. So like, for example, verbs tend to be heads a lot. So if it's a verb, this second term here would give a high score to the verb. Whereas determiners are almost never heads. Things like the and are almost never heads. So they would get a very low score according to this. So it's a pretty simple equation. But it works quite well. And they even just optimize the likelihood of getting the parent right. No structured training whatsoever. So this is a local model where you just select each word, but then you have a global decoding using a minimum spanning tree algorithm at the end. So another thing that I should mention here is that this model is really, really simple and works quite well. It didn't just work quite well out of the box. There was actually a very nice presentation by the person who came up with this model, Tim Dozat, where he mentioned, oh, I tuned this model super well, and that gave me like 3 extra points of accuracy or something like this. So I think the reason why this model is successful is, number one, it's a good model in the first place, and number two, it was tuned very heavily to work well. Given the sizes, what embeddings they use, et cetera. So are there any questions so far? It's pretty simple models, especially compared to the transition-based models. Another thing I should mention, I'm presenting this as a dependency parsing model, but you can use this as a model for any sort of relation extraction, like calculating relations as well. So, you know, if you wanted to do relation extraction between words, you could similarly have a by affine model where you were trying to predict whether a relation existed or not in this case. Okay, so global training. In previous work, there was margin-based global training, local probabilistic training. I talked about both of these. There's also a nice trick that you can do to get global probabilistic models for these kind of dependency structures. So basically what you would want to do, this is a recap from our previous thing, where you would want to have a score for each tree, and then you would divide by summing over all of the trees. And obviously we can't do this because the space of all possible trees is exponential. But there are actually nice algorithms within graph-based parsing that allow you to calculate this partition function using dynamic programs. So you don't actually have to explicitly expand all of this and enumerate over all of them. So for projective parsing, the Eisner algorithm, which I mentioned before, is a bottom-up algorithm for dependencies. In this, you can actually, you can calculate this partition function and train the model exactly by calculating this and then maximizing the probability of the correct tree. For non-projective parsing, there's something called the matrix tree theorem that can compute marginals over any directed graph. I won't go into the details here because it's a little bit beyond the scope of what I feel like I should be explaining here. But it's a really nice algorithm, and basically it also works in matrix, like basically matrix manipulations. So it's very easy to implement in any of your neural network toolkits, et cetera. So, and this was applied to neural models by Maxima here. So you can reference his paper and take a look at how he used it to train. Okay. So up until now, I've been talking about methods for dependency parsing. So dependency parsing is good for dependencies between words. It can also be used for anything where you want a graph out of a sentence, where the graph edges are the words, the relations between the words. Phrase structure parsing, on the other hand, as I mentioned before, is good for when you want kind of a tree that's defined as spans over the sentence. So there are also models to calculate phrase structure. So phrase structure parsing are models to calculate phrase structure. And there's one important insight that parsing is similar to tagging. And tagging essentially is the search in a graph for the best path through the graph. In other words, you can come up with a lattice where each edge in the lattice is a part of speech tag. And the Viterbi algorithm or the forward-backward algorithm are dynamic programming algorithms that go forward through the lattice and calculate the probabilities of the edges, and then backward to retrieve the best path. On the other hand, parsing is the search in a hypergraph for the best tree. And I will define this in a second. But one thing I want to stress here is even if you're not interested in syntactic parsing at all, this concept of hypergraphs is something that can be very useful. And it has been used for other things like translation or semantic parsing, et cetera. So how many people have heard of like hypergraphs or have an idea of what they are? Nobody, okay. So this might have been something that we used to teach in algorithms for NLP, but don't anymore. It's a pretty neat concept. I won't be able to go into huge amounts of detail on it, but I like this concept a lot. And basically, in a hypergraph is something that is a graph that has a degree, and the degree of an edge is equal to the number of children a specific edge has. So if we think of a tree, we can think of for example, sorry, I'm missing a word here for some reason. That should be I. I have disappeared, I guess. So this should be preposition to I, or past tense verb to saw. So you can see that this node here has a single child. On the other hand, this node here, this is a verb phrase, and it has a left child of a past tense verb and a right child of a noun phrase. And you can also come up with another verb phrase that has a past tense verb, a noun phrase, and a prepositional phrase. So this is an edge of degree 1, this is an edge of degree 2, this is an edge of degree 3. So the degree of a hypergraph is the maximum degree of any of the edges in the graph. And a graph, a regular graph that we're all familiar with our graph search algorithms, our graph traversal algorithms, is a graph with a hyperedge, a graph with a degree 1. So what is a dependency tree? What is the degree of a dependency tree? Any ideas? Yeah, essentially, you can view it as a graph of degree 1. So that's part of the reason why we can do the Chulu-Edmonds algorithm over it. We represent it as a graph, and we use a standard graph algorithm over it. And each head has can have multiple edges. Another way you could view it is you could say the maximum degree of a dependency tree is a maximum degree of a dependency tree is the maximum number of childs of any head. That would be another way to look at it. So this was kind of a trick question. You can view it either way. But you could either view it as a graph of degree 1 where each head has multiple edges, or you could view it as a graph, a hypergraph of degree, like maximum number of children where each head has a single edge. So an example of a graph of degree 1 would be a simple graph that kind of looks like this, where you can step through and go from node 0 to node 2, node 1 to node 3, etc. So the reason why hypergraphs are kind of interesting is they can be used as a way to represent ambiguity in parsers. So essentially, if we have, I saw a girl with a telescope. Sorry, I'm missing. I feel like I'm missing a slide here, but like, we have the parse. I have a girl with a telescope, and there's two interpretations of this here. I saw a girl with a telescope where you saw the girl using a telescope can be viewed as the tree that has the red edge in it and doesn't have any of the blue edges in it. So basically, the verb phrase has saw, it has a girl, and it has with a telescope as separate phrases. On the other hand, if you choose the blue edges here, you get saw, and then you get a girl with a telescope as a noun phrase. So essentially, what I want to show here is a lot of the structure in this tree, all of the black edges are shared between either of these two parses. So this allows you to essentially share parts of the tree that are the same, but express ambiguity based on different edges that you can have here. So weighted hypergraphs are like graphs. where you can add weights to the hypergraph edges. And generally, these weights can be equal to something like a negative log probability or some score of how likely that particular edge is. So an example, um, the, the weight of this edge up here would be the weight of going from a sentence to a noun phrase and a verb phrase, maybe conditioned on this particular context. The weight of this hyperedge here would be the weight of going from a verb phrase to verb, noun, prepositional phrase, maybe conditioned on this particular context, etc. So we give weights to each of these edges. And the CKY algorithm, which I presume a lot of people know from essentially, in NLP class, maybe algorithms for NLP otherwise, is essentially a way to find the highest scoring tree given context-free grammar. And you can view it in a way of creating a hypergraph of containing all candidates for a binarized grammar and then doing a hypergraph search. So essentially the way this works is it's almost exactly the same as the Viterbi algorithm. So if you remember the Viterbi algorithm, the way the Viterbi algorithm works is you have a graph, and iteratively, as you walk forward through the graph, you calculate the best path up to a particular node, right? So the Viterbi algorithm, you step forward. At each point, you calculate the best score of a particular node in a graph. And then based on this, you step through and iteratively calculate the best score. So you can do exactly the same thing in a hypergraph, with the only difference that the Viterbi algorithm is over graphs of degree 1. So graphs of degree 1 only have one previous best score here. So if you remember the Viterbi algorithm, basically what you do is you add the best score plus the weight of the edge. In a hypergraph, you just add the best score from n previous children, where n is the degree of the edge that you're considering. So you can find the score of following edge 1 to be the score, essentially, the best scores up to here, and the score of the edge. And if you have edge 2, you calculate the score of this edge and add together all of the best scores. So then to disambiguate and find which of these edges you should be following, you then take the min of these two scores, and this will give you the best edge for this particular node. And then you can calculate the best score is the score of the best edge. So as I said, this is analogous to the Viterbi algorithm. In fact, it's almost exactly the same. The only difference being that in the Viterbi algorithm, you only have one score here. But when you're searching over a hypergraph, you have multiple scores here. So I'm sorry, I realize I'm missing a couple slides and I went over this relatively quickly. But hopefully the general idea is clear here. Are there any kind of are there any questions or clarifications that I could do? Okay. I think, so one way you could think about this is the CKY algorithm is basically creating all these hyperedges for a span and the two children that go into creating that span. So basically the CKY algorithm would be actually search over a graph of degree 2, where this is the left child and this is the right child, and then this is the weight of the edge that you're using. So hopefully that also is another parallel that you can make. So you can also, over a hypergraph, you can also calculate the partition function. In other words, you can calculate the overall probability of any trees that you can get. so you can find the marginal probability of each span, or given a CFG grammar, where the partition function is the probability of the top span. So this is the same as the normal CKY algorithm or normal hypergraph search, except we, instead of taking the max here, we take the instead of taking the min here, for example, we take the sum of the probabilities, or the log sum x of the probabilities. So why is this good? The reason why this is good is this then allows us to do things like global training. So let's say we wanted to do global training of a parser model. We could calculate the score of the or the log probability of the correct span, the correct tree, the log probability of all of the other trees using this dynamic programming algorithm, and make our loss function in our neural network, for example, the log probability of this minus the log probability of the partition function. And that would allow us to train the model. So this is analogous to the forward-backward algorithm, but the forward-backward algorithm is over graphs. This is called the inside-outside algorithm. It's basically a generalization of the forward-backward algorithm that allows you to do hypergraphs, to do graphs with degree of more than one. Okay. So why did I need to cover all of this? The reason why I needed to cover all of this is because there are methods that use this in neural models to train them. And they're actually quite simple to implement. They might not be super simple to implement efficiently, but they're quite simple to implement. So basically what you can do is neural CRF parsing. So this is basically a tree-structured conditional random field model, as opposed to the linear conditional random field model that we talked about before. So for example, what can we do? We can predict the score of each span using maybe a feed-forward network or maybe an LSTM or something like that. And then we can do discrete structured inference using the CKY and the inside-outside algorithm. So this is a paper from 2015, so they didn't just throw an LSTM at it because we didn't have throw an LSTM at it until 2016. So what they did was essentially they had templates and they did neural feature combination over the templates. But the basic idea is essentially these probabilities that we calculate over each edge are calculated with a neural network. And because these probabilities are calculated with a neural network, we then do the inside-outside algorithm, or maybe the inside algorithm, based on this neural network. And then we feed this into our loss function, and then we can backpropagate all the way into the function that calculates these probabilities over the spans. So what this means is now, essentially we can completely optimize our dynamic programming algorithm that will allow us to do parsing in this way. So is this kind of clear on a high level? Are there any questions or things that people would like to clarify? No? Okay. So there's an even simpler model, which is just a span labeling model. And the basic idea of this is you try to decide whether a span is a constituent in a tree or not. And the idea here is essentially we know that this is a span in the tree. This is a sentence span. This is a noun phrase span. This is a, it's not a single span in a constituent, but it covers multiple spans. We have another thing like that over here. And then we gradually can split up these spans as we go down. The basic idea here is they train a they train a predictor that takes in the span and tries to predict its label and whether it's a span at all or not. And then they simply step over all of the potential splits in the tree and find the split with the maximum probability. So maybe they say this span here of noun phrase into not has the highest probability, so we split here. Then they step down into this and say, okay, now this has the highest probability. This split has the highest probability. They step down into this, they split this, etc., all the way down to the tree. So this actually gives you a parsing algorithm that's linear time in the, no, sorry, quadratic time, because you need to choose the number of splits. But it gives you an efficient algorithm that can essentially just step down the tree and do splits. This allows for various loss functions, like a local versus a structured one, or inference algorithms like a CKY versus a top-down one. And one of the interesting things they show in this paper is that actually if you have a really strong feature extractor like an LSTM or something like this, you can get away with relatively simple loss functions and inference algorithms. So there's one kind of interesting thing that you should definitely be aware of, which is as our methods for extracting features get better and better, essentially, like as we get large pre-trained models and things like this, the marginal utility of more complicated structured prediction algorithms seems to be decreasing. So for example, if you have, there was an example where when we went from old feature-based models to new neural network models, the third order parser was actually worse than the second order parser, the second order neural parser. And you can actually show that like as we go to LSTMs as feature extractors, now suddenly the gain we get from structure is smaller and smaller. So I think the actually you can get away with relatively simple things and still get competitive accuracy. Maybe not quite as good as the structured models, but still get competitive accuracy now. That being said, I suspect that this is not true for the more complicated cases. So I feel like we had an example last time where there's a particular difficult phenomenon of noun-verb agreement where you have lots of distractors in the middle. And these kind of things, like the overall perplexity, when you measure the overall perplexity, it's not, there's not a big difference in the perplexity between the two models. But these specific phenomena that require you to capture syntax well really depend on you having a nice syntactically motivated model. And I suspect that that's the case here, although I haven't seen a really strong empirical evaluation that shows that. Okay. Any questions or? Okay. So I'll move on to a second one. There's an alternative of parse re-ranking, and basically it's very often the case that you could come up with a really nice model, but it's hard to implement a dynamic programming based decoding algorithm. So what you can do is you can try re-ranking the output of a simpler model. So you generate with an easy to decode model, rescore with your proposed model. And there's a bunch of examples of this. This is also good if you're, no matter what you're predicting, essentially, even if it's like relations, if you're doing relation extraction, if you're doing even question answering, you might not be able to search over all of the possible hypotheses. Search. If you're doing search, you might not be able to search over all the documents with a complicated model, so you get a first pass. So there's a lot of examples of this. So there's a model called inside-outside recursive neural networks, which you can't easily decode with. But so they generated with a more traditional model and rescored with it. Um, there's also a method of parsing is language modeling and recurrent neural network grammars. So these are both kind of generative models of parsing that are not easy to decode with. So they generated with a discriminative parser and then rescored it with a generative model. But whenever you're using re-ranking, not together with parsing, there is a slight word of caution. And the reason why is because re-ranking can also be viewed as implicit ensembling. And what I mean by this is there, let's say this is the space of outputs that you can generate from your discriminative model or like your easy to decode model. And this is the space of outputs that you can generate with your more complicated model. So in reality, your easy to decode model will generate all kinds of things. Your more complicated model, yeah. So your easy to decode model will generate all kinds of things, and maybe coincidentally, this one had the highest probability, so your accuracy is not super high. And then you run your re-ranker, and your re-ranker says, "Oh, I like this output." So then suddenly your score goes up, right? It might be. This might actually be an effect of the fact that you're essentially combining together two models. You have your re-ranking model, and you have your easy to decode model, and they're both. They both have different structures, they were trained with different parameters, et cetera. Then if you actually generated things with your more complicated model, it might be the case that the one with the highest probability actually wouldn't have been really good. So if you do re-ranking with your like nice, super well motivated model, you need to be careful about overstating the fact that it does better in a re-ranking based setup. Because the easy to decode model prints down the search space, and the re-ranking model chooses only the best parse in this space. And there's a nice examination of this by Fried et al., who basically take a discriminative model and a generative model, and they generate candidates. They go through a lot of trouble to generate from the more complicated model. They come up with a clever inference algorithm, et cetera. And as a result, the original scores reported in the paper that proposed the generative model are essentially these ones. And based on that, they said the generative model, hey, it's doing re-ranking, it's improving, so it's probably a better model. But in fact, if you decode with the generative model, you get scores that are significantly worse. So this is just a thing that you should be careful about when making claims in this space. Okay, so I guess that's all I have for today. That's ending a bit earlier than normal, but are there any final questions about parsing or things like this? Okay, I will finish up then. So thanks a lot.